Hello everyone, welcome to Marri Reddy Institute of Technology and Management, Mlritm Dundigal, Hyderabad. So this is S. Rajkumar, working as an assistant professor for the Department of Electrical and Electronics Engineering. So in this today lecture, I am going to explain the introduction to locus diagrams. So here, before going to take a introduction to locus diagram, what is locus diagram and what is here in this lecture, the topics to be covered: introduction to locus diagram and locus diagram per RL series circuit. So I am going to explain the locus diagram for RL series circuit. So in this RL series circuit, so depending upon constant and variable element. So first case I am considering, that is variable resistance and constant inductive circuit. So here you can see, so by considering RLC circuit, so what actually locus diagram is. So here we can define the what is locus diagram is the locus of extremities of current phasor obtained for various values of variable element is called locus diagram. For example, if we are considering any circuit, if one of the circuit element, in that circuit elements, so one of the circuit element is variable, then depending upon this variable circuit element, the value of a circuit or characteristics of a circuit is changes or varies. So as the value of variable element is changes, the circuit parameters just like current, power factor and power consumed by the circuit is also changes. So depending upon the variable element, by varying the element of a circuit, the current is changes, power factor is changes, power consumed by the circuit is also changes. So this change, if you are taking a current, the current phasor of a circuit, by varying the variable element in a particular circuit, the locus, if you are drawing a locus of the current phasor, so that extremity point of a current phasor, so obtained for the variable element by various values of a variable element in a given circuit. So that extremity, the tip of that current phasor for variable values of a variable element in a given circuit is called locus diagram. That diagram obtained by the varying the variable element in particularly current phasor of a given circuit. So that we call it as that we defined as a locus diagram. So that such a graphical approach obtained for variable locus diagram helps in predetermining the characteristics of AC circuit under different conditions. So this is a helping of a locus diagram. So locus diagram helps in order to predetermine the operating characteristics of a AC circuits under different circuit conditions. So this is the meaning of locus diagram. So next we will consider locus diagram for series RLC circuit. Well, I am considering a series RLC circuit, for example. So this is a series RLC circuit. Here, so alternating current voltage. So constant alternating current voltage is applied. So alternating current with a fixed frequency. The frequency is also fixed in the alternating voltage. So this is alternating voltage. Here this R is variable. Here in this case R, resistance is variable in RLC series circuit. So this inductance. So this inductive, XL is the inductive reactance, XL is the inductance, RL inductance. So this inductance is fixed or constant. The variable R is varying. The resistance is varying in RLC series circuit. So this is a circuit diagram I am considering. So for this circuit diagram, I am going to draw how to draw a locus diagram particular RLC series circuit. So here you can see. So this is a RLC series circuit I am considering. to obtain the locus diagram, it is necessary to have a one variable. So we need to consider one variable element in a given circuit or LC series circuit. Here resistance I am considering as a variable element. So remaining inductance, so that is inductive reactance, that inductance I am considering as a constant value. To analyze the two, so either we can change the resistance or either we can change the inductance of a RLC series circuit. I am considering first case as a element or can be variable. So or can be variable, that is resistance R is varying and constant XL, that is inductance I am considering as a constant, resistance as a variable element in RLC circuit in order to draw the locus diagram. So for this RLC series circuit, the locus diagram, so for that one I am going to consider RLC circuit as I said. So R is varying and inductance is constant in this circuit. So here we can see for in an inductive circuit, for any RLC circuit in inductive circuit, so the current inductive current, the current always lags the voltage by 90 degrees. If you are taking a pure inductive, if V as a reference, so current is lagging with respect to the voltage. So here that phase angle, how much it is lagging, how much the current phasor is lagging is given by phase angle. The phase angle is equals tan inverse inductive reactance by resistance for a given value of variable resistance R. So this is the case. So current here in RLC circuit, current IL is inductive current is lagging behind the voltage by a phase angle of theta is equal or phi is equals tan inverse XL by R for a given value of R. So here we can see for I am considering for resistance value is equals to 0. So if resistance is equals to 0, when R is equals to 0, we can see that the current is maximum. The current is maximum, that value is given by V by XL. So this V by XL, the maximum current is lies along the x-axis with a phase angle is equals to 90 degrees. So that we can see in a phasor diagram, in a locus diagram or a phasor diagram. So when R is equals to 0, current is maximum. This maximum current lies along the current axis. So that is nothing but a current axis with a phase angle of 90 degrees. So if we are keep on increasing the resistance value, so here in this circuit R is the variable. That's why I am varying the resistance value. So when R is increased from 0 value to infinity, so if you are increasing the resistance value in a circuit from 0 to infinity, the current is reduces. If when R is equals to 0, current is maximum V by XL. So phase angle is equals to 90. When R is equals increases from 0 to infinity, the current gradually reduces from the maximum value V by XL to 0. The phase angle is also reduces from 90 degrees to 0 phase angle. So this is the case. When R is 0, the current is maximum. The maximum value of current is given by applied voltage by inductive reactance XL. So this maximum current lies along the current axis with a phase angle of 90. If when R is increased from 0 to infinity, current is also gradually reduces from maximum value to 0 and phase angle is also reduces from 90 degrees to 0 phase angle. As we can see from the figure, the tip of the current. So the tip of the current vector traced by the path is a semicircle. This can be seen in a circuit diagram as shown in figure. Here, so I am considering, so this is the current axis. So axis of a current. So this is a applied voltage axis. So when R is equals to 0, the current is maximum. The maximum value of current is voltage, applied voltage by inductive reactance. So if we are increasing, the resistance value, variable resistance is increases from 0 to infinity. So infinity, the current is, so here the current is also, here you can see the current gradually reduces. So the current gradually reduces to, So this is the tip of a current vector phasor. So it is reduces, the phase angle is also reduces to 0. So when R is equals to 0, the phase angle is 90, the current is maximum, the maximum value of current is given by V by XL. So when current is reduces to 0, so R is changes from 0 to infinity, the current is reduces gradually. So from maximum value V by XL to 0 value, the phase angle is also reduces from 90 degrees to 0 degrees phase angle. So this is the, this is the variation of a current phasor in RLC circuit when current variable resistance R or with a fixed resistance or inductance of inductive reactance XL. So this is the current phasor. The phasor current is changing with respect to a variable resistance R in a given RLC circuit. So this is the circuit diagram. So corresponding relations or corresponding equations we can say. So related equations we can see now. So related equations of a circuit. As usual, we know that the current, the inductive current is given by IL is equals voltage by impedance of a circuit. In our AC circuits, the voltage by impedance of a circuit is the current in a given circuit. IL is the current in a given circuit or current through the variable inductance of a RLC circuit. So from that circuit, so we can write from that phasor diagram. So from that phasor, so as I said, so voltage as a reference, the current is lagging with respect to the voltage by some angle. That angle is given by tan inverse. So that angle is nothing but a phase angle. The phase angle is given by tan inverse inductive reactance by resistance. So with this phasor diagram we can write it. So from this circuit also, this phasor diagram itself, so sin theta is equals XL by Z. So Z is equals, from this Z is equals XL by sin theta. So whereas cos theta is equals, from this phasor diagram only, from cos theta is equals R by Z, resistance by impedance. Therefore we are substituting sin theta cos theta is equals here V by XL sin theta. So this is the current through the inductance of a RLC circuit or current in a series RLC circuit. In a series RLC circuit, the current is same. Series circuit, the current is same. So current IL is equals V by XL into sin theta. So for here, so applied voltage is constant. The inductive reactance and the inductance element is constant in RLC circuit. Only resistance R is variable resistance I am consider. So for constant V and constant XL, inductive reactance XL, so the above expression for IL is the polar equation of a circle. So with the diameter V by XL as shown in figure. So this is the polar equation of a circle. So here next we can see some more equations related to the variable resistance and fixed reactance of a RLC series circuit. Here Ix, X component, here X and Y coordinates of a RLC circuit is given by, X component is given by IL sin theta, Y component is given by IL cos theta. So from the above relations, so Ix is equals V by ZL, V by Z and XL by Z. So by this equation V XL by Z square. Let us consider this is the equation 1. So similarly, so by substituting the above equations, the Y component of a RLC series circuit is given by V by Z times R by Z, where IL is the V by Z, cos theta is the R by Z. So by substituting the above equations, so Y component of current phasor is given by VR by Z square. Let us consider this is the equation 2. So in order to get a circle equation, so the above equation, squaring and adding the above equations, above two equation 1 and 2, squaring and adding the above two equations. So we are getting I of x square plus y x square is equals, so v2 square into XL square plus R square by Z power 4. So V square Z square. This equation can be simplified by V square Z square by Z4. V square by Z square. From this is, let us consider this is the equation 3. So from this equation, so circle equation for the RLC circuit, we can see that circle equation. From equation 1, Z square is equals to Vxl by Ix, and substituting this equation in the above equation number 3. So whatever we are obtained finally, so this is the equation number 3. So if you are substituting this equation number 3 in this equation number 3 in place of Z square, so the equation number 3 becomes Ix square plus Iy square is equals to V square by Vxl by Ix. So by simplifying this equation, we can get V by XL times the Ix, or we can write, so if we are bringing this right hand side constant is equals left side, Ix square plus Iy square minus of V by XL in times Ix is equals to 0. So here, in order to get a complete circle equation, so circle equation, so we are adding another term V by 2 XL square. So this we are adding for the above two sides, left hand and right hand side. The above equation can be written as Ix minus V by 2 XL square plus Iy square is equals to V by 2 XL square. So finally, so what we are getting, so the final equation by substituting the all above equations. So this is the final equation number 4 is the final equation, that is Ix minus V by 2 XL whole square plus Iy square is equals V by 2 XL whole square. So this is the final equation. So the above equation represents a circle, right? So we are representing, this is in the form of a circle. So this is a standard equation. So we can compare this equation with a standard equation. We know that x minus x1 whole square plus y minus y1 whole square is equals some radius r square. So this is the standard equation of a circle. So if we are comparing equation number 4, so with a standard equation of a circle equation, then we can get the radius of V by 2 XL and with its coordinates of the center. So V by 2 XL comma 0. So these are the coordinates of a center. This is the radius of a circle. If we are comparing equation number 4, so this equation number 4 is represents a circle in case of series RLC circuit when variable R and constant XL. So inductance is constant, resistance is varying in RL series circuit. So this is the radius of a circuit. So this is the coordinates of a center of a given circuit. So here this is the lecture taken from the reference of this is from the Google. So this is all about the locus. What is the meaning of, in this lecture we are covered what is the locus diagram. So locus diagram is nothing but a extremity of a current phasor, so that we call it as a locus diagram. So how to draw the locus diagram for a series RLC circuit. So we have seen these two topics in this lecture. So with this one, thank you all. Thank you very much.